My name is John Kilbride. I'm a remote sensing scientist at Renoster. And probably about 8 months ago, I got an opportunity to be a beta tester for the Alpha Earth's Foundation's Geospatial Embedding Fields product. Uh, I really think this is an exciting new data product, and I've been pretty, excited to share it with people and try it on new tasks. And I think it's going to be useful to a lot of people that are doing forest structure mapping or working with carbon on a fairly regular basis. So with that, I'm going to dive into my presentation here. All right, hopefully that's up. All right, and I do want to say throughout this, I will try to periodically look at the chat in case anybody has questions. Catherine Malcolm, who basically helps run Renoster, is going to be hanging out in the chat. And if you have any questions or any logistical considerations, she will be there and she can answer questions. All right, so let's dive into this. This presentation builds on material from a blog post I wrote for the Google Earth and Google Earth Engine Medium blog channel. So if this is interesting, this is kind of this article provides a longer form discussion of the same stuff. And for the second half of this presentation, I am going to cover kind of the technical materials that were covered at the end of that blog post. So again, more information if you want to follow along with this. There is a link to the GitHub. This is in the article. Whoops. Oh, it's going crazy now. I'm going to just put this in the chat, this link here. Sure, this is very
I just
exciting.
popped that article link in there for you, Jack.
Oh, yeah, perfect. Thank you very much.
You got GitHub. Cool.
All right, so I'll put that in there. The reason I'm just sharing that is my understanding is some people might want to try to follow along live. I will say if you are doing this, I would encourage you to try to get the Conda environment configured, just because this will have. Is the chat on the screen? Sorry, I'm new to this. No.
Yes, we've got it. Yep.
Okay, perfect.
We can see it. Thanks.
All right. All right, anyway, so follow along with the technical. If you want to follow along, make sure you have this Conda environment configured. Otherwise, what I'd encourage you to maybe do is just watch as I go through it and talk a little bit about it, and then you can follow along on your own time later. We are going to release the recording at some point on LinkedIn shortly after this. All right, so in terms of what I'm going to talk about today, I want to answer what are geospatial embedding fields, and I want to talk about the sorts of problems that they address with DMRV workflows. I want to talk a little bit about how they're generated, although these do involve fairly complicated models, and so I'm not going to get too into the weeds of this. There's just a kind of an important high-level point that I think it's worth highlighting. And then lastly, I'm going to talk about how these can be used in practice. So I think it's worth starting off from the perspective of what is a normal remote sensing workflow? In terms of what's the paradigm probably the majority of people kind of making land cover or forest structure maps are operating within? Well, there's kind of just a fixed set of steps most of us go through. First, you're going to get a bunch of reference observations. So here I'm showing, forest inventory plot locations. For carbon, you're oftentimes dealing with one of two things. It's photo interpretations of usually change. You're trying to do change mapping, or you've got forest inventory plots that are giving you estimates of structure. Sometimes it's other stuff like you're bootstrapping off LiDAR or JEDI. You're then going to go out and you're going to aggregate a set of data layers that describe the landscape. So this could be your Sentinel backscatter, like I'm showing here. This could be Landsat, your ensemble of remote sensing metrics. You aggregate all of these different data layers together. You perform a big old intersection. You take your points, you smack the observations on top of the data layers. You get your response value from your reference. You get your features from these data layers. And then you fit a statistical model to actually estimate the thing you're interested in. And then you apply it everywhere. And so this is kind of the most normal remote sensing workflow I can think of. Parts of this probably for what you're doing are a little different, but in general, this is kind of the paradigm we're all operating in if you want to get pixel level estimates of something. So what are geospatial embedding fields then, and how do they slot into what I just described? The slightly technical jargon-laden definition I came up with, but I think it's a good one, is a spatially continuous latent space that encodes semantic, environmental, and contextual properties at each location. And to go through that a little bit, embedding fields are spatially continuous in the sense that over some domain of interest, you have wall-to-wall information. You can, regardless of where you go, it's like a continuous raster layer that you can always find an observation for within a domain. Some people are now building these not for the entire planet, but for just, certain regions. So within some area, it's spatially continuous. It's a latent space in that it represents the distillation of information by a deep neural network. So you have a whole bunch of input data. I guess the information on this side would be things like your satellite predictors, and they're going to get boiled down into some sort of compressed representation. So you've got a spatially continuous kind of compressed space produced by a model, and it's encoding semantic, environmental, and contextual properties. So in the abstract, if I could give you a set of data layers that I told you were very generically good, what would you hope these would encode? Well, some of it is going to be the environmental side of things, which is kind of like, well, literally what's at the location you're looking at. Is it a forest? Kind of what's the structural density of it? Is it mature? There's that sort of information. There's also more abstract stuff about kind of like, how does this pixel associate with the broader patch on the landscape around it? So, these embedding fields, we hope, are kind of, they're this compressed latent space that is encoding a whole bunch of properties that we find desirable and generically descriptive of each location. So that's kind of what they are in an abstract sense. In a much more practical sense, they're a global raster data set. So these are annual global layers with a 10-meter spatial resolution. And they basically are kind of like hyperspectral data in that they have 64 channels that you can operate on. These were produced from 2017 to 2025. I know 2025 was in production right now. I don't know if it's actually out yet. I assume it is. And this was, it is documented at length in a research paper here. This research paper is also linked in the blog post, and I'm sure if you're here, you've probably likely seen it. So kind of continuing on in terms of what these things are, beyond like literally, they're a set of statistical features, and literally they're like raster layers. They represent an extension of geospatial foundation models in general. Ever since the foundation model trend kicked off, which I guess is an extension of the kind of pre-training stuff that was big before that, or was kind of the hot topic before that, people have been trying to get geospatial foundation models kind of running for remote sensing applications. So SAT-MAE was kind of the first one of these architectures. And typically, these are very large neural networks that you can go and download. And if you configure your data to feed through them, you can basically, kind of not necessarily create embeddings, but you can operate on the data. The idea being, they're giving you the model and then you can feed data through it. Geospatial embedding fields are kind of a different paradigm. Instead of giving you the model, they're giving you the applied results, the latent space everywhere. So you don't ever actually have to touch the deep learning model that exists in the background. And this is really useful for two reasons. First of all, geospatial foundation models are really hard to use. I'm sure if somebody here has like tried to rig one of these up, you've probably found this. I know that the Alpha Earth team had a dedicated team member that basically just focused on getting other competing architectures to work. It was a labor-intensive process. And so existing models are not easy to deploy. And so if you're not like a deep learning savant, they're not particularly easy to just pick up and run with. And then additionally, they're really expensive to run. Like these are big models and they require lots of data. And so you've got to set up a pipeline that's potentially not going to be cheap to actually operate with. And so by kind of pre-applying these and releasing these as data layers, this makes this really accessible compared to kind of other models that existed in this geospatial foundation model space. So in terms of DMRV, what does a workflow look like, an image processing workflow, beyond kind of that high-level descriptor that I was providing before? Well, oftentimes it looks something like this. It's like a long, awful flowchart. And ultimately, as analysts and as kind of scientists in this space, typically we're really interested in like the end result of this whole process. We want to understand like the distribution of some ecological variable in space. We don't necessarily want to be spending all of our time monkeying with data to get there. And unfortunately, with satellite data fusion ensembles, you have to do a lot of that. There's a lot of, you aggregate your raw data, you've got to apply a bunch of filtering steps, you put it through feature engineering steps. And all of this is to ultimately get to the same goal as the embedding fields, which is a set of features that have this contextual environmental descriptions. But, because we're not being guided by like a learning process, kind of like the model is when it's being fit. You just have to compute the whole kitchen sink of everything and then use feature selection to sort it out after the fact. So lots of aggregating, statistical feature extraction. It's a good amount of work. And it's oftentimes black magic-y too. You have to know where satellite processing recipes work. Like there are some places on Earth that certain algorithms work pretty well. There are other places that are more data limited where they break down in kind of strange ways. And the only way to know this stuff is to actually, kind of have experience with it yourself. So that puts us in an undesirable situation where, you have to have a lot of knowledge to do this. And a lot of it is like not necessarily like useful scientific knowledge. It's more like you just have to kind of know the minutia of the data. And so embedding fields seem like a nice solution to this because they're pre-cooking this encoding process and kind of getting rid of this black magic step. And it's also preventing you from having to like set up a pipeline to do all of this data processing internally at your company, where you have to maybe host a whole bunch of intermediate layers and whatnot while you feed your data through to get your feature fusion stuff at the end of it. Alpha Earth features can be downloaded pretty easily through Google Cloud Storage. You can also access them in Google Earth Engine trivially. And they offer, out of the box, really strong performance in low signal to noise ratio areas. So this is an image of three of the channels from the geospatial embedding fields over Colombia. Colombia is an incredibly noisy region. And if you've ever worked here, it's one of the cloudiest areas on Earth, the west coast of Colombia, comparable to kind of like the Congo in Africa. And getting like spatially, temporally stable features to do time series analysis is non-trivial here. And the fact that you can kind of just open up these embeddings and start working, and you're kind of getting the same juice you would get out of a custom pipeline, is an enormous time saver. It allows really rapid iteration and testing of ideas. And I'd say that this is like a key benefit of these things. My colleague who works and lives in Colombia had LiDAR transects, and we were interested in doing forest height mapping. In about an hour, he was able to send me these rasterized transects. I was able to sample them, build a data set from these embedding fields, and then apply it with a random forest model. This whole process took probably an hour. I did it in a coffee shop, and we were able to get an intermediate product that we could use to evaluate, like, does this seem like this is going to be a viable approach for the analysis we were considering? And it didn't take much effort. Doing this with Sentinel-1, for example, and having to process all the data to ARD and go through all of that, I mean, it would have had to have been a funded research project for us to have taken that on. So it's really useful for this, for rapid prototyping. Well, actually, one last point I want to say on this. The ability for it to work in data sparse areas is super important because many well-known image processing recipes aren't particularly stable in a lot of places that are more data limited. So for example, in Southeast Asia, the techniques that work there are kind of different than what you'll see or the ones that work the best are different in a lot of other areas. And so this again gets to kind of that black box nature. This was what convinced me that these things were a really useful tool. I was kind of shocked when I saw this. I didn't expect this model to work nearly as well as it did. All right. So before we get to the technical demonstration kind of side of things, I want to just go over a little bit of how these embedding fields are generated. I'm going to keep this at a high level because ultimately the models that are used here are fairly complicated, and I don't know if there'd be a ton of benefit of me sitting here and going through the architecture like step by step. If you want to do this, I would encourage you to look at the Alpha Earth paper, as well as they cite a bunch of other papers in there that explain specifically how these like spatial, temporal, convolution blocks and stuff work. So if you're interested in that, sorry, I'm not going to get into that today. The key thing I want to highlight is that all of these, the key ingredient in general behind these geospatial foundation model is self-supervised learning. And so this is a general paradigm wherein we find it is oftentimes easy to get input data to these models. It is very hard to get good outputs for them. Collecting forest inventory plots is pretty hard. Collecting satellite data everywhere, comparatively kind of easy. It's pretty hard to, but you get what I'm saying. So self-supervised learning is all about learning off of the data itself. The most common scheme for this is you're going to take a whole bunch of satellite images and you're going to obfuscate some part of the input. So here you can see for this image up here, they've held out these two parts of the image. And during training, you have this information compression part. This is kind of that creation of the latent space. And then the model plays a game where it has to try to reconstruct the parts of the inputs it didn't see during training. So by playing this game over and over again, the model, in theory, gets really good at learning to compress this input information into a very efficient representation. So that's self-supervised learning. In terms of how it comes into play with Alpha Earth specifically, there's this nice diagram in the paper. You have multiple satellite time series. The three that Alpha Earth operate on, the primary ones, are Landsat, Sentinel-2, and Sentinel-1. Sentinel-1 radar data, it kind of always acquires measurements. So it can kind of be thought of as being represented by this darker line here. Each dot is a measurement and they're obtained regularly. The observations from Landsat, though, are sometimes obfuscated by clouds. And so you're getting kind of this periodic set of observations. They're slightly more irregular on these other tracks. What Alpha Earth does is it's going to aggregate these multiple satellite image time series over a given time period. It's going to summarize them and then give you a summary period for, just a single year. So they kind of outline this more. And when it takes this input period and learns to kind of construct embeddings for this valid period, the way it's being trained is they have a whole set of reconstruction targets. So for example, if you're feeding in some of the satellite time series, some of the images might be withheld and they'll have to be learned and reconstructed by the network. They also have other variables in here for reconstruction targets, such as Jedi metrics, grace gravity fields, other things. The idea being all of this diversity of tasks is going to force the encoded representation here to be more diverse. It's going to have to encode more information about the landscape and be more generic, and then hopefully more useful for a variety of downstream tasks. So this is just specifically in the Alpha Earth diagram. The most relevant chunk for what I'm going to talk about is the top bit. And what you can see is if you go off of what I was describing in this figure of each of these are an individual time series, you can see you have your individual satellite time series here, such as Sentinel and Landsat. They're getting encoded together. So this is kind of the creation of an initial latent space that's specific to each sensor. You then glue those together to create kind of this overall latent space. There's a little bit more going on here, to be honest. But anyway, you eventually get to your latent space. And then this is where you do the evaluation for the various reconstruction targets. So this is kind of the essence of what's going on. I will say Alpha Earth also has co-training with a large language model as well as a student-teacher framework that is kind of involved in the training. And so this makes it like kind of complicated, and that's what the other parts of the diagram get to. I will say that this is kind of the key ingredient in my mind. The other stuff are kind of variations on this idea. And I want to highlight, I think that it's an open question as to how you actually train these things and build them at the moment. We just started making them. Tessera is another global 10-meter embedding field product. However, instead of using the same reconstruction-based approach, they use a different contrastive approach called Barlow twins. And so, but you can see that based on even the diagram here, if you kind of like squint your eyes, you can see it's a similar idea, which is you have a time series, it's being transformed, you're building out a latent space, and then eventually, you're doing something to train it in a self-supervised manner. Here it's contrastive learning. In the other case, it was reconstruction of targets. I think it's going to be an open question. Like I said, what's the best way to do this? Which sorts of approaches result in the best, task agnostic embedding? So these are embeddings that would be good for, in theory, any downstream task. Maybe there are ways of doing this that are better for specific ones. So, for example, it could be that including kind of less context from things like climate metrics as reconstruction targets is better for localized phenomenon. I think that this we'll begin to see this, and I'll say that I think this will also be explored extensively, and people are like I said, trying to create localized versions of these. So maybe like a Mexico specific embedding model, for example, as opposed to one for the entire planet. All right. So now I want to give a little demonstration from the article of what you can actually do with these things in practice. The workflow for the analysis is here. What we're going to be doing is generating a LiDAR derived canopy height models, or well, what I should say is we're going to be creating a model that estimates forest canopy height from the alpha Earth embeddings. And we're going to parameterize this using some LiDAR canopy height models I generated over the state of Maine. This is going to proceed in 3 stages. This is how it was structured in the article, and it's also how the code is structured. The first step in this is going to be the construction of the modeling data set. The second bit is going to be actually fitting the canopy height model. And then the final bit is going to be application of the fitted model. Throughout this demonstration, I will say there isn't a whole ton for me to necessarily do. So I will simply be commenting on some of the more meta decisions that were made, as well as what you might consider as an analyst while working with similar data. For the most part, I'm just going to be hitting the run button. All right. So the first thing I want to just start off with is explaining some context of where the data is coming from in all of this. I used USGS 3-depth LiDAR data. We use this data extensively at Renoster for estimating carbon stocks. LiDAR is airborne laser scanning data. Our friends up north call it airborne laser scanning. The LiDAR data is probably the best. It's probably the most accurate way you can measure forests at any sort of scale. And for obtaining height, it's probably the most objective method, short of somebody actually climbing to the top of the tree and dropping a tape down. So it's a pretty good, it's a great source of data to extrapolate from, because we've kind of minimized the amount of response error that we can have. We don't have a whole lot of error from like students trying to take vertical height measurements. In terms of processing nodes, I developed these layers using a software package called Laser that I would highly recommend. It has both R and Python bindings. These are just the 95th percentile of the height returns above a 2-meter threshold, which is pretty normal for the area. And finally, before as a final like post-processing step, I used the NLCD layers to basically mask out any areas that were not forested or had not been labeled forested recently. So this is now a layer that we can sample off of to get pseudo plot locations that or LiDAR plots that we can train off of. I didn't put all this in the tutorial just because I feel like this would be a little overly long for a blog post about the embedding fields. But if anyone has questions about the underlying LiDAR data, I'd be happy to answer it at the end. Okay. So the first thing we'll do is we'll actually build the modeling data set. In theory, I think everybody should hopefully be getting the same results because I think I set the seeds to make this reproducible. What we're going to do is simply grab 5,000 points. This right now, we're kind of emulating what is a very common situation, I think, when doing anything related to carbon, which is you have some good data for part of a spatial domain, and you're interested in building out a model such that you can extrapolate to the rest of the state. There is LiDAR data over the rest of the state here. I just didn't include it so that we would have something to like fill out for our example. It makes it more fun, I think. So I'm going to go to the Google Earth Engine script that does the sampling here. And I'm going to have to switch tabs because I got to do it on the right account. And Catherine, I don't want to put you on the spot too bad. Could you just confirm, can you see my screen as I've transitioned here to like a code browser?
Yes. Yep, we can see
excellent. Thank you. All right. So in the end, the code here is pretty simple. By the way, I understand that this is eyeball-searingly white, so I apologize. Using the Alpha Earth embeddings in Google Earth Engine is very, very simple. Or it's called embedding. They are simply an image collection that you need to import. each image, each year's worth of data is tiled up. So you can load that in, mosaic it together, and then you can kind of just treat it like any other raster layer. So, in terms of actually running this logic, like I said, there's not a ton for me to demonstrate here other than I'm going to hit run and it's going to execute the sampling. All this script is doing is it is loading in my forest height mass, which I have here. That. So you can see this is a layer that is masked out over the state of, over chunks of the state of Maine. Here we go. Areas that are not forested have been masked out. The vast majority of the state of Maine is forested, especially the northern parts. And so we're going to simply take a random sample of this. When I created this layer, the only other thing I will note is if I click at any given location, you can see that I have included in my underlying reference data both the height as well as the year. So at each point location, when we run our sampling, we can obtain what the height was, as well as what year this was taken, so we know what year to then go get the embedding fields for. So the script does exactly that. It's going to just take a simple random sample of these height measurement values, and then it is going to go and it's going to get the embeddings that are spatially and temporally coincident with each of those points. It is then going to dump this out as a CSV to Google Drive. So if I hit run on this, I've already
Oh,
run
hey,
this
Jack.
once. Oh yeah.
Oh, sorry, real quick. I think we're actually looking at the wrong screen.
Oh.
I think we're looking at GitHub, not the GEE.
Oh, bummer. Okay, sorry about that. Let me just quickly do. Let me try resharing my screen. Can you see everything now?
Okay, now we're at Google
There
Earth
should be
Engine.
too much pink on the screen.
Yes, there's a bunch of
Okay,
pink.
perfect.
Yeah, now we're in GE.
Okay, excellent. All right, sorry about that, everyone. All right, excellent. So yes, as I was trying to say, sorry, you have this first step here where you're going to run the sampling of the forest data. This is, this basically just a simple random sampling. And then you're going to sample the embedding field values. There isn't a whole ton for me to show in this script. It is basically just a simple sampling one, but I suppose I will explain the logic of it. Yes. All right. That's all I basically have to say there. The key thing, though, is so the only features I'm grabbing is I'm just taking the alpha Earth embeddings from a single year. Okie dokie. So once we've done that, this will export to your Google Drive. It should just dump out as a CSV. Let's see. Anyway, it'll appear in your drive somewhere. You got to go track it down into where it spits out. You can Control F the file name, this forest height data set. I have already downloaded mine into a local folder. So the next thing we'll do after we've built out this data set, we have obtained these 5,000 point locations. We're going to go through the process of actually fitting the model. And there's kind of some more interesting stuff that happens here. We're going to use an ElasticNet regression model. I'll explain why in a little bit. I should say ElasticNet is basically just a linear regression model. It just has some regularization terms on it that allow it to do variable selection. And this is a tool that works very well, in my experience, with the embedding fields. You have to tune, when you fit these models, you have to kind of tune some of the hyperparameters. And so we're going to be doing that using a combination of spatial cross-validation as well as the Optuna software library. So I will click on this link quickly. This time we are going to be using a Google Note or a Jupyter notebook. This can be obtained from the repository. I've got this loaded up over here. And once you open this and you get into it, the steps we're going to take are first, we will define our kind of just file input outputs. This generates some figures as well in the logic. And so you will have to set this to wherever you want on your computer. on my computer. My name is John. So I have this, I have cloned the project repository to my desktop. And then I downloaded and put that spreadsheet that was produced, our sampling data set, in there. Really quickly, if I go up to the top here, I just got to run all the cells of this notebook. There's a whole bunch of functions and whatnot that have been defined. I'm just going to execute all of these. If I print out the first couple rows of this modeling data frame, we can see we have all of these embeddings. These have these names like A0 or A5, A6, A7, all up to A64. There are 64 of them. A stands for axis. Each of these can be thought of as kind of an orthogonal axis to some extent of a multidimensional space. And then we also have our height and our year. We don't actually use the year anymore at this point. So height is kind of the thing we're most concerned with. And like I said, we'll define a couple image paths here. This is just stuff that gets dumped out. Mostly I used in the article, but if you want to regenerate it yourself, you can. So the next thing we need to do is when you do hyper or model parameter selection, when you're doing tuning and fitting a model, typically there are knobs you have to turn. And so for ElasticNet, there are two key considerations. I will say very confusingly, the names of these parameters are almost exactly the opposite between the two most famous implementations for whatever reason. I don't know why they chose to do that. But what the parameters represent, so instead of getting bogged down in the names, you have the strength of the regularization as well as the mixing of two kind of types of regularization that are being used. So you've got to decide kind of what those are. You've got to set them. And so the way I'm going to do this is we'll use cross-validation, where I will take some of my data points, I will take a hyperparameter combination, I'll fit a model, and then I'll evaluate it on withheld data. And in doing that, that'll give me an idea of how well that configuration did. I can repeat that a couple times, shuffling out the data I'm using to train and evaluate to get an average. And if I try that for a bunch of combinations, it'll give me an ability to pick, a set that seems to perform the best on unseen data. Now, of course, a big consideration for us as ecological scientists is spatial autocorrelation. The default of assumption of cross-validation is that the data that is in the testing set is independent of the data in the training set. If they aren't independent, your estimates from the process kind of break down. The logic that governs their validity breaks down. So what we do to account for kind of and so to build on that or to continue, what happens with natural systems is you have spatial autocorrelation. And so observations that are close to each other are actually not independent. They're pseudo-replicates of one another. And this is problematic for cross-validation. So a strategy that's very common is to use spatial cross-validation. This picture right here is not particularly good, so I'm going to go back to my slides because it doesn't look right. What you can see is that we've basically laid a grid over the landscape that was 25 meters by 25 meters. And we've assigned points to each of these grid cells, and we've assigned then all those points to one of 5 folds. So all the observations in here are either going to be used together or held out together, but they're not going to be kind of like, this point isn't going to ever be compared against this other point that's super close. One consideration that I didn't get into in the blog post is, well, how do you decide how big you make the spatial cross-validation grid? And it turns out that's actually like a whole can of worms. It's a kind of a difficult question, and you have to kind of like look at the data a whole lot. And so I will freely admit that I simply wanted to indicate that you should probably think about, spatial cross-validation. So I chose 25 meters. I didn't rigorously assess that. I'm going to fully admit that. But I would assess it. But in general, use something like that. I will say I know a lot of people prefer to use R. There's an excellent package called Block CV. And then spatial K-fold is kind of like the discount Python version of it. So Block CV is really great if you want to do this in R. Before we do modeling, what we're going to do here is now define what is our dependent variable, which is obviously height, as well as our independent variables. It's all of our alpha Earth columns. Nothing particularly surprising here. And then we're going to get into actually running Optuna. I'm not going to get into a huge overview of exactly what Optuna is, other than I will say it is a very useful hyperparameter optimization library. It is really simple to configure and get working, and it tends to behave pretty nicely with deep neural networks, which some other libraries don't. The key thing here is basically what I've done is with Optuna, you get to define an objective function. This is like the goal. What are you trying to get out of this process? If I go up to that really quickly, I just want to highlight where is my Optuna objective function? Right here. The key thing I want to highlight, and this is what happens in every trial. I think as I put it in the things, this is Bayesian optimization with a tree parson estimator. It is really just like guess and check wearing sunglasses. It's just cool guess and check. And so basically what you do is, Optuna will select it gets informed based on the previous trials it does. It's looking for the best combination, but it'll pick two of the parameters we're interested in from a range of values. It's going to run an iteration of cross-validation, and it's going to return the average score. And based on how well we did, the algorithm is going to tweak what it picks for the next one. So it is just really iterative guess and check. This has the advantage of using Optuna and similar libraries. I figured it'd be useful to demonstrate it. Where this becomes especially nice is, if you have a lot of parameters to optimize. So like if you're using gradient boosting, this is pretty useful because you need to search through a pretty large area. And doing that without some sort of a search algorithm can be a little inefficient. All right. So I think that covers most of the details here. We've set up a cross-validation grid. We're going to run Optuna. And then, well, I suppose I should just do this now. All right, run that. And I think this will run it goes pretty fast. Again, what we're evaluating in the background here is just a whole bunch of linear models. So this is doing basically kind of like least squares just over and over again. So it'll go quite quick. As it progresses along, it will update you as to what the best value it finds is. And because this is a linear model, it's worth considering what is like the actual form that we're getting out here. Well, it's just going to be a set of numbers. It's going to be the 64 coefficients associated with each embedding field value. And then it's going to be an intercept term. So it's 65 numbers. The reason I decided to highlight elastic net regression in this tutorial is that there are a lot of, for example, Renoster is a commercial user of Google Earth Engine. So we're conscious of our compute usage. We want to make sure we're not like burning too much money. Also, I will say they now have introduced individual compute limits. So I have a separate account that I use for conducting research with my peers. And with that account, I think you now are limited to, unless you have kind of a contributor tier thing, you only have like 1,000 compute hours every year or something like that. So ElasticNet, as I'll demonstrate, is really efficient to use. You can use elastic net regression to fit either, you can fit general linear models with it. So you could do classification. You can also do regression. And because it's just basically multiplying every single alpha Earth embedding pixel value by one of those 64 numbers and then adding everything up, it's very, very cheap and efficient to apply over a large area. The one time I ran it over main and exported it with kind of the current set of logic, I was able to classify at a 10-meter resolution an area the size of Maine for about $25. That is, I mean, you're going to have trouble getting too much cheaper than that for most VM-based solutions, especially if you're doing any level of actual like feature engineering on top of that. All right, so our training here is almost done. One last point, I'm working on something I hopefully will submit as like a write-up, but I will note, in general, elastic net regression tends to get you a good amount of the juice, so to speak, out of the embedding fields. Fitting a more complicated model, such as a tree-based model like random forests or gradient boosting, it'll get you a little bit more performance in most of my tests. So like your R squared will go up a couple more points. Your RMSE will go down a little bit. For height, you're not going to go down by an entire point, but you might go from like 2 to 2 point, or from 2.5 to 2. So it's a small difference, but it is at a pretty big computational cost. So our optimization process completed, one of the things that I pointed out in the article is it turns out the best combination here is we're basically just doing regular old regression. The fact that this alpha term here is close to zero basically means the ElasticNet part of ElasticNet was like turned off. So we're just using all of the information. And this is indicative and kind of a sign that the embeddings are in some way working. We would expect that, if each embedding had some value and was different than the other embeddings, in theory, throwing some of them out wouldn't be useful. They'd all be kind of useful. So this is somewhat suggestive of that fact. We then proceeded to do a whole bunch of cross-validation, and we can get a one-to-one plot. So what you're seeing here is this is the observed LiDAR height. We have our predictions from our regression model. And the way I've created this is I basically ran a single iteration of cross-validation. And these are the points here are when the observations were in the test set, if you're a nerd about how to make a graph like that. The R squared of 0.62, obviously, what's a good score? Well, one's the best score, but 0.62 is quite good, I would say. Maine is a really, like a surprisingly structurally complicated state. I think a lot of people underestimate the Northeast in terms of its difficulty in working. There's a huge amount of structural variation. There's very long, complex disturbance legacies, and there's a lot of mixed species environments. And so it's a tough area for remote sensing models to work generally. You can't rely on regional averages and have the model be particularly stable in your predictor space in a sense. And so I think 0.62 is pretty good. I will say, like I said, I haven't formalized my other comparisons. I have found that the alpha Earth embeddings do consistently about a bit better than a conventional feature ensemble that includes like SAR and stuff. It does a little bit better on average, and both of these approaches get about the same error. And so I'm pretty impressed with this score. The last thing I did here, do I have a slide on? Oh, I'll get to this in a second. This is a visualization. Oops, sorry, of the values of all of the coefficients that. So basically to get your final number, what this is saying is you're going to take the value of this embedding, you're going to multiply it by this amount, and then sum it with this embedding multiplied by that. And so I'll get into this in a little bit, but it's interesting to see which embeddings have the biggest coefficients, because these are the ones that are kind of the most important to driving the final output relationship. And then finally, for our third script that I'm going to jump to next, the last little component here is we've got to bring our model to Google Earth Engine. That's kind of tricky to do with random forest, but with a linear model, it's pretty simple. I have the code formatted so it literally spits out the model here. You literally can just copy and paste these coefficients into the Earth Engine script I'm about to show you, and you're off to the races. So when I say you could do classification as well, you would just take, you'd fit up here in the top of the script a classification linear model, and the output is still going to be the same. It's going to be just this. There is just one, you add on the logit transformation or whatever you're doing. So it's a pretty compact representation of the entire model, which is pretty nice. I'm going to boot up the final script here. Again, this one is just a JavaScript script. So you just need to copy and paste this into your browser. And one thing you'll notice quickly is that the code to make the legend, oops, sorry, let me open one more tab. Yeah, the code to make the legend here is actually longer than the code to do the model application. So with the linear model, like I said, applying this boils down to you take the alpha Earth embeddings and you multiply each of them by the numbers in this list. You sum them all up, and then you add the intercept. So that's all this is doing. And you can see the inference procedure is pretty dang quick. It's almost instantaneous. Do that. We can see that the model, at the very least at first blush, seems to conform with what we'd expect. This portion of the state, the down east region, is less productive. We should have some smaller trees there. Trees over in this area of the state are, typically bigger. You're getting into kind of larger hardwoods. And then you kind of have a lot of commercially, stuff on fast rotations up here. So you'd expect smaller trees. So this is good at first look. It seems like it's capturing the general trends pretty well. If we zoom in and I turn on my satellite layer here, we can see it seems to do quite a good job of capturing these patch edges with fitting your own convolutional neural networks. This can be tricky. Getting sharp patch edges is always like a little bit of a rabbit hole. Convolutional neural networks in particular have a real incentive to kind of blur things with how they learn their feature hierarchies. So anyway, we're looking around. This looks like pretty decent. Certainly these stands, when I look at the satellite imagery, seem more mature and dense. And we're seeing that these are getting mapped with higher values. However, we are seeing one thing that's kind of a classic sign of neural network stuff. There's a little bit of tiling. There's kind of these tiling artifacts. Um, these are an artifact of that image distillation process. If I zoom out, sometimes what you can see is borders on the landscape. So for example, as you go from, the way these models work is it processes about a 1 kilometer chunk and it'll make this, and then you step over and you process the next one. Between the versions of this, they've actually gotten better. They did a lot of they accepted feedback and basically improved their outputs so that they're smoother now. You still find them every now and then, but this kind of like very faint checkerboarding at a high resolution, that's kind of just an artifact of how these neural networks seem to process information. This is kind of, I think, a point of work going forward. And I will say, oftentimes, in the carbon space, you know, we're oftentimes working at a resolution lower than 10 meters. So at Renoster, we oftentimes do things at 26 because that gives us the same size pixel in terms of area as forest inventory plots we have in the region. Oftentimes we do 30 because that's just the native resolution of Landsat. If you downscale these alpha Earth embeddings or the prediction maps produced from them, like if I downscaled this to 30 meters, most of this goes away. And so I will just highlight that ultimately 10 meters is very high resolution. It's actually higher than the nominal resolutions of most of the input data, all of the input data. In fact, Sentinel-1, has like roughly a 20-meter resolution in reality. So that's kind of what these things look like. They're quite impressive, man. I'm thoroughly impressed by this, and this framework of kind of using these linear models is very fast for getting things fitted quickly, and it has the benefit of the difference in this map between using random forests in the linear model is pretty negligible, but the difference in cost is like an order of magnitude. It's several $100 to run a 10-meter random forest model across the entire state. So that's why I chose to highlight using ElasticNet. All right, let me go back to my slide deck. I think we're winding down here. All right, so we've applied that. Oh, one thing I just wanted to highlight, visualizing these coefficients, like I said, you can find what the biggest one is. What I did is in the article is I took the coefficients with the biggest magnitudes. These are bolded here, so 24, 39, and 55. And then I visualized this as an RGB image. And it's pretty cool. It's a good way to find like what's a combination of bands that seems to really maximize the diversity of the variable I'm interested in. And so I'll be interested to try this again, where what happens if, for example, I'm interested in change and I visualize, the coefficients with the biggest values for that. It'll be interesting to see. It's a good way to kind of slice, 64-dimensional data. So that was just kind of a thing I threw in there. And then I kind of wanted to end on this. So I've been talking about how, embedding fields are kind of like potentially a new paradigm for doing satellite pre-processing. It allows us to automate things. So they're like new, but at the same time, they are from an analyst's perspective, I think like radically the same. They experience a lot of the exact, these really are drop-in replacements for your existing feature engineering pipelines. And they come with the exact same analytical quirks and considerations that traditional metrics do. For example, you can see in 2024, as well as other things, kind of this line along the corner of northeastern Maine, northeastern Maine. I just can't do my compass direction. No, this is northwestern Maine. This line does not correspond to any biophysical phenomenon. This is not land ownership. This is just the edge of, I would have to double check exactly where it is. This is either a Landsat scene or a SAR scene edge. And what you're seeing is kind of, there's presumably a slightly different distribution in the scenes that were over here versus over here, maybe their distribution in terms of how many observations they have, and we now have, some artifacting. And this will show up then in the resulting map. And so the same considerations you probably have had about how, I need to make sure my maps are temporally and stable, you kind of will probably have to do similar post-processing work here. I don't think that that's going away. This is more just getting rid of the need to have a gigantic pipeline you're maintaining on your own. Um, I'll also note this. I won't scroll through my whole slide deck because I think that makes people nauseous. But if I go back up to this figure here, ask yourself, just before I switch off, well, I guess I'm giving it away on the slides here. What doesn't this process fully encode? You're taking all of this satellite information and you're distilling it down through this reconstructive process. What aren't you going to get through this process? And the answer is probably a lot of things. First of all, there's plenty of variables you might be interested in that may not be adequately represented by these reconstruction targets. So there could be value in including ancillary information there. We're also only encoding information over about a 1-year period, or I guess it's like a 2-year period. There are many ecological processes where you need a longer term perspective than this. My advisor during my PhD was Robert Kennedy, who did the land trender algorithm. And so, this is his whole thing, is categorizing long-term change, but including information in biophysical models of forest structure about the timing and the location and the intensity of past disturbances in many areas like Oregon, for example. I mean, that's like key to the game for estimating above ground biomass, because your trees are so big and your spectral signals saturate so quickly. You kind of have to know how long ago something was harvested to clue into like, well, how much biomass should I be allocating here? These embeddings are going to struggle to do that because they don't include, 30 years of data. They're only including a recent summary. Fortunately, these are all just raster layers, and there's like nothing that says that you can't take, first of all, embedding fields from 2 different embedding field models and just slam them together. But you can also take the embedding fields. This is kind of the approach we take at Renoster. We assume that these embedding fields are going to do a good job encoding the majority of like your pixel percentile type metrics, your texture, your spectral summaries. You can then add on to that additional metrics, such as land trender derived disturbance, to kind of fully complete your metric space so that you have a good model. So that is a limitation, and I know that this is something that's also under consideration for the next generation of these embedding field models. Is people are interested in trying to include, like, how can we include in these embeddings, that like longer 20-30 year time perspective as well as just the recent stuff. So that'll be exciting to see as well. Specifically, the person who did the Geotessera models talked about that, I think, in a podcast or something I listened to. All right, I think that's basically everything I have about the embedding fields here. I hope everybody got something out of this. I'd be happy to take some questions. I'll be here for another. Well, I guess I'll be here until the hour, but if people have questions, I'd be happy to hang around a little bit longer.
Awesome. There are a couple of questions already in the Q&A, John. If you can see them, let me know. Otherwise, I can read them out loud to you too.
Sweet. Do you mind reading them out to me?
Yeah,
Sorry, I
yeah.
don't want to.
No problem. We got one from Gabriel. What is the magnitude of the improvement in predictive power when using embedding fields relative to using a carefully set of more typical predictive layers, NDVI, etc.? They need to be large enough to compensate for the use of super black box products.
It's not a huge. Here, I will show you. I want to put I'm gonna caveat this by saying these are early results, so these are not like totally done. I am working on a comparison over Maine with similar data. It's not quite the same as what I did in the article. So I have a figure that kind of shows this. So let me see if I can get this up. Is this the one I'm looking for? Okay. Can you see the graph? Is the graph visible, Catherine, right now?
Yes.
Okay.
Yep.
There's a lot going on here, and so I'm going to here, I'll do this. Oh, well, that didn't work. I was going to try to hide this side of it. this is across different cross-validation grid sizes in the state of Maine. What you're seeing here is this is the RMSE for height of the conventional ensemble. So this would be Landsat, HLS Sentinel 2 percentiles, Landtrender stabilized, spectral reflectance, Landtrender disturbance history, SAR texture metrics, and whatnot. So it's a pretty comprehensive ensemble. And then these are two other geospatial foundation models. And so it's a it's a meaningful improvement, and it does seem like they maybe can extrapolate a little more stably. But this is kind of when I was saying, radically the same. I think that this is a much easier way to squeeze all the predictive juice out of these features without having to maintain a pipeline. It's not necessarily clear to me at the moment that um, these are going to like radically beat out a conventional ensemble that's been well designed. The big area where I think that this would result in more meaningful improvements is in data sparse areas like I was highlighting, like in Colombia or the Congo. Those are areas where building a feature processing pipeline can be so challenging that you probably are leaving performance on the table, whereas these are soaking it up. But in Maine or in the United States and Europe, people have been hammering this stuff for so long. We kind of know how to squeeze most of the energy out of it. So anyway, I hope that answers your question, and hopefully that this is correct. Like I said, these are early results, although this was based on quite a lot of numerical runs. So
Awesome. We've got a couple more. Next one up, would you ever use lat long as inputs in your model to improve performance?
um, man, it's a really good question. Before, when I was trying previous versions of those results I was showing, I included Latin long at one point, and it was far and away the most important predictive feature, or jumped up in importance really high. Um, I I think it kind of depends on how you go about modeling. I think the short version of it would be it depends on how I'm validating my maps. Um, I think including lat and long can sometimes make the problem of spatial autocorrelation worse by including that as a predictor. And so the challenge there is this makes getting like convincing results from spatial cross-validation at times more tricky. I get I'm like being very nebulous in how I'm phrasing this because it kind of depends on the data. If I was doing design-based inference, though, like I had FIA plots that were like a probability sample of the landscape. Um, when you do validation through that paradigm, spatial autocorrelation in your predictive features isn't as big of a concern because of how randomness is being induced by the sampling design. And so if I was doing it there, I would probably be more willing to throw lat and long into the mix as covariates. They will bring down model performance. I guess the question is whether you can convince yourself that that improvement is genuinely corresponding to like a meaningful increase in the model's extrapolation ability.
All right, great. And then one more. How do you associate reference data to embedding data when embedding data is only annual, especially a variable like canopy height can vary within the same year? For example, if a harvest happens during growing season.
This is really good, and this is actually probably something that is probably some noise I introduced into the tutorial. What I did, and especially now for the analysis results, the more recent ones with the box plots I was just showing, I first of all of the LiDAR data I used it's the same leaf off data, so it was always acquired kind of during the same time period of year. So it stabilizes a little bit for that. And I used the swath geometries to spatially map out the year like each height pixel was flown. And so in the cases where some LiDAR acquisitions are acquired over two leaf-off seasons, So like you might acquire some data at the end of 2016 and then some data over the rest of the area of interest over the next year. When I did that, now what I do is I try to keep track. I spatially map out the different areas when they were flown to make sure I'm associating that height value with the correct year's worth of the embedding field value. I will say, though, that does become a little bit of a game, and you are right about this in that you do have to be careful when doing these automated sampling and probably take more steps than I illustrated because you will have cases where what if you have a leaf off measurement from the spring and in Maine they do forest harvesting over the winter? Now it's like, well, do you associate the embedding with the year after, like the summer that's coming up or the summer of the previous year? That can be a little bit tricky. And I guess my only point on this that I would have as a suggestion is a lot of times if I sample like I did in this demonstration of I'm taking a huge sample of a large landscape, a really useful tactic is fit the model to all of the data points and then look at the errors over each individual data point. And that can be a useful way if you look at like what areas have big training errors. You can find pixels where maybe you made a mistake in terms of you sample like you have a situation where you sampled from the wrong year, and you can at least clean those examples out of your data set. But it is a little bit fraught. And so I guess I tried to do it based on the timings in the USGS swath geometries. That was a very long answer. I apologize if that's like got a little lost in the weeds there.
Great. Well, there are no more questions, and we are at time. If anyone has any last minute ones and they want to stick around, feel free to put them in the Q&A. Otherwise, John, great job. Thanks for running us through that. And we'll be sure to send the recording to everybody. Oh, we have one final one.
Excellent.
You get to stick around? Okay.
Yeah.
Can you train multiple versions of the model and look at the error rate between multiple models to determine where the model has uncertainty?
Yes. I would say there are kind of two approaches to that. It's funny. I have a colleague that like just recently asked like a really similar question. The There are two ways of kind of like looking at this. You could absolutely train multiple models, apply them multiple times, and then like you're saying, look at the uncertainty to try and figure out like, is this an area where the model is breaking down? I think my first line of attack would actually be sorry. What's this called? I think they're called area. Area of applicability mask. Sorry. I will put this. Maybe I will send this out afterwards if I can't find it. I believe they're called area of applicability masks, but that might not be the exact name. But basically, what you're trying to do with these. Oh, I'm bummed I can't find this at the moment. All right, anyway, I'll stop trying to find it. This is a methodology where what you can do is you basically look at the feature space and you say, I have a whole bunch of reference observations and I've collected, data in these feature, I have points in this feature space. I'm going to make a prediction at a new location. Is that location, in terms of its features, similar to locations where I've made predictions in the past or where I have reference data? With the idea being of like, if you have a cloud of reference points right here, if you have a point that falls in the middle of it, you're probably comfortable making a prediction. If you have one right on the edge of it, well, you'll still make a prediction. But like once you have a point that's like well outside of anything you've ever predicted before, um, um, you probably want to flag that as a location where maybe I just shouldn't make a prediction here. And that's what those area of applicability masks do. It's a method for constructing them. And I think that this is a little bit better because models can be very confidently wrong. And sometimes when they fail, they can be wrong in a very similar manner. And so if you just look at like, do the predictions of different models look different? There may be areas where the model is wrong, but it's consistently certain in how it's wrong, even across cross-validation. And I don't know. So because of that, I think I would maybe start with an approach that looks at like, the distribution of the training data set versus any candidate point. You can also do this using something, they do this in structurally guided sampling, like their motivation for doing it is different, but there's a whole area called structurally guided sampling for building out sampling data sets that does stuff like this. I think they use something called like Mahalanobis distance or something. It's a way of checking that. So anyway, again, perhaps a too long of an answer, but that would probably be my first approach for that problem.
You have one more, and then we'll probably just wrap up after that.
Okay.
But if people have additional questions, you can email us. We'll send you the recording, and you can reply back with questions there. But final one for the live session. If a feature importance analysis identifies specific alpha Earth embeddings as primary predictors for ecological measures in region A, how can we assess if these embeddings represent universal ecological signatures versus site-specific spectral characteristics before applying the model to region B?
This is a really good thing, and I think that this is I would say the simple answer is, as far as I know, you can't. Um, my understanding is that, in having played around with these a little bit, is because these are taking all the information at different geographic locales and kind of boiling them down into that latent space. Uh, I don't necessarily think that, like, I'm trying to think about this. Like, if you have like a deciduous forest in Maine, in one of the embedding fields is like zero point 0.6. I don't think if you go to like another area on Earth and you're in a forest and the embedding field value for that same channel is zero point 0.6, that it's going to mean the same thing. They're kind of like, all these numbers are kind of interacting with one another. And so as you move across the landscape, that those interactions seem to change. And so how this would manifest in mapping, for example, is um, when doing stuff with my buddy in Colombia, we had data at the southern portion of the state. And I noticed that if we tried to apply data kind of up through the rest of the west coast of Colombia, the model performance would geographically begin to break down. And it's because eventually kind of like the feature relationships just eroded at a distance. And so one thing I will just quickly highlight is, in my example I was doing here, um, you know, a key component of this is that this area of Maine, despite all of the climate gradients, is overall pretty well represented by all of this other area. And so I would be comfortable building an alpha Earth model and extrapolating into this area. What I would not be as comfortable doing would be like if I had this data set and I started extrapolating in this direction. Because I do think at a certain point you get to a point where just your model performance will break down. I don't know if I can formalize this more, but I do think that this is going to be an ongoing point of like, how can we maybe build embedding fields that are, have that sort of stability you're talking about. Like some features are spatial, but some of them are more like intrinsic, if that like makes sense. Like they represent something more fundamental and stable. Um, so anyway, hopefully that kind of answered that point.
Fantastic. Yeah, that's it. Thanks so much,
Excellent.
everybody, for joining. Really appreciate it. And again, thanks to John for running us through the tutorial. And yeah, we'll send you the recording later today.
Excellent. Thank you guys so much for attending.